Okay, here we are on part 2, and we're looking again at volumes that have equal cross sections. The first one we did, the equal cross sections were squares. So it does want to do this one to show you it doesn't have to be squares. It could be isosceles triangles or equilateral triangles. This one happens to be rectangles. So it could be any shape that we find. So this one, the base of our figure, is enclosed between this function and y equals 0. That's the x-axis. The cross sections perpendicular to the x-axis are rectangles twice as high as the side in the xy plane. So let's make some sense of that. And when I sketched, or I put that one in the calculator, and it turned out to be parabolic, and it crossed at -6 and 6, and it went like this. And we are trying to figure, this is the base, the area enclosed between that graph and the x-axis, y equals 0. And rising out of it this time are rectangles. So if I was going to draw one here, this would be the base of what it's standing on. And it would rise up twice as high as that is wide toward you. However, I get the task of drawing that. So it's coming up towards you, or toward out of the page, we'll say. And this is 2 times this. Alright, so mine's kind of bending back a little bit. I'll try to draw a better one here. Alright, this is the base, this rectangle, twice as high as that, coming up. A little better. It's hard to draw. And they're getting smaller. And down here, tiny, tiny little rectangles. And that's going to go all the way from front to back. So it's going to create, there's going to be an infinite number of them. And it's going to create a figure, not a whole lot unlike the first one, just taller relative, and has a different shape on the bottom. So anyway, that is my picture of it. Not so good, is it? Alright, all these rectangles are going to stack up and create this 3D figure, rising up with imagine an infinite number of these obeying these commands, and you will have that figure in your mind. So the calculus is easier to do than the artistic rendering. Alright, I'll take this one and we'll talk about that. So I'm going to add these up across this figure, and they're going to add from -6 to +6, but it's very symmetrical. So I'm going to use my doubling trick and only go from 0 to 6, doubling the volume on this side to get the entire figure. So now I need to know the area, or I'm sorry, the volume of one of these rectangles. So if I look at it over here, it has a thickness, and that thickness is very thin, infinitesimally thin, but I can read it on the x-axis, so it's a dx. And this value is going to be right there, hooking to my function. I went over x and up y. So one of the dimensions is y, but the problem states that the height is twice the width, so we have y times 2y. So that ends up, I can take the 2 across the integral sign where it combines with the 2 that I put there, creating a 4, and it leaves me y squared dx. I need to work in x, so I go back and I see y can be replaced with this expression, so I will do that. Alright, I stopped, dropped, and rolled over to my calculator. I could square this, and if I was in the part of a test where I didn't have access to the calculator, I could square this and integrate each term. It would not be impossible, but I wanted to get the joy of getting to the answer quickly and checking it to see if I'd set it up correctly. And when I put this into the calculator, it came out to be 1024 over 5, which was bing, 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 correct. All right, so that's units cubed. All right, so hopefully this will guide your thinking on any kind of cross-section that the problem will throw at you. All right, class, carry on.